So, what we're going to talk about today is the next step in our description of motion in our kinematics unit. And what we want to talk about is the concept of speed versus velocity. Because a lot of people think that these are exact synonyms of one another and they use them interchangeably. Now we know that they're both measured in the same units. So in physics, where we're using the metric system, that's going to be meters per second is our general unit for speed and velocity. That doesn't mean that they are the same quantity. In the same way that distance and displacement, although they are both measured in meters, are not the same quantity. So let's go from there. So we'll look at an example. So forgive me for a second for a pretty terrible drawing, but there we go. All right. So what is that? Now, I know you may say it's some sort of like sick looking chicken, but it is not. I'll just erase that. That is a terrible map of New York State. So, Scarsdale is kind of out here. Once again, really terrible map. Never claimed to be good at drawing. And we're going to be talking about going here. So, if you don't know where that is, that's about Binghamton. So, it's where I went to college. So, I know the trip up to Binghamton pretty well. So, two ways to go. We can go up Route 87 to exit 16, and then you get off there and you go on Route 86, formerly Route 17, through the Catskills, and there you go. And we'll call that path one. The other path you can go down across the George Washington Bridge, down Route 80 through New Jersey to the Delaware Water Gap. Then it becomes, I believe, 380 all the way to Scranton. And then you take this road up here, which I believe is 281 or 81. I forget which one it is. Anyway, this is path two. So some information about path one and path two. Here you go. Path one, the distance, meaning the length of the path for path one is about 180 miles. And the time it generally takes me when I travel along that path is about 3.5 hours. All right. Then we talk path two. That's a little bit longer of a path. D2 is equal to 200 miles. But generally, when I drive that path and I don't get too much traffic, the time is actually a bit shorter, about 3 hours. And you might say, well, how is that possible? Well, it just so happens that this stretch of road in Pennsylvania has a very different speed limit than this stretch of road in New York. And this road is monitored very heavily by the New York State troopers. If you've ever driven up to Cornell or Binghamton, there's lore there about everyone getting speeding tickets, and that is very true, by the way. Whereas these path through New Jersey and Pennsylvania, in my experience, the troopers there are not so boisterous in their giving of tickets, so people tend to go a little bit faster there. So let's just use that data. So if I were to ask you the question then, how fast, let me actually go onto a new piece of paper. How fast did I travel on path one? Okay. And so if we were to calculate that, how would you do that? So stop the video for a second, think about it, maybe do that calculation. All right. Now you're back with me. Hopefully what you said is what I would do is I would take the distance for path one. So I'll just write this down in equation format, divided by the time for path one, and do that. And I don't know what's over here, but that's probably what I would do to answer the question, how fast? And that would be 180 miles over 3.5 hours, because we always have an equation, plug in with units, and then an answer with units. That's about 51.4 miles per hour. Okay. Now, think about that. 51.4 miles per hour is how fast I traveled on path one. Something something sounds off about that, right? Um, because that seems to suggest that at all points in time, I traveled 51.4 miles per hour along path one. And that's simply not true. As we know, if we just go back here, if you've ever made that trip before, you know, you have to go across the Tappan Zee Bridge. There's exits to deal with. There might be traffic. There might be construction. The thought that you would be going 51.4 miles per hour for the entire trip feels wrong. And so that's a problem. So this question, how fast do they travel on path one, is actually a really flawed question. But 51.4 miles per hour does say something about path one. What does it mean? So stop the video, think if you can think about it. Hopefully, what you said is that that represents the average speed for path one. So I'm going to write that down. Average speed for path one. Um, I could write that down here. Hopefully you remember what is the notation that means average. That's using the bar on top of the quantity. We're not going to use a variable for speed for reasons that I can explain another time, but I'm just going to write the word speed out. So that says the average speed for path one is 51.4 miles an hour. So that's not making the claim that I'm traveling 51.4 miles per hour at all points on that path, but overall, I'm traveling at 51.4 miles per hour for that path, right? So let's talk about that average speed. What is it explaining? What it's not saying, so this is what it's not saying, you go this speed the entire time. Okay. What it is saying is that this is the one speed you would have to travel to go that distance in that time. Okay. Or a way of thinking about it, it's like sort of like a holistic speed for the trip, sort of like not dealing with all the individual moments, but dealing overall with the trip itself, right? So thinking about it like an overall trip speed. Okay. Now, going back to this, why do we take distance divided by time? Well, the concept here, speed is a scalar, and we want to be basing speed based on other scalar quantities, specifically distance and time. All right. So apart from average speed, as we said, at all different moments, you would be traveling at different speeds. So we want to give a word to that, and that is what is called instantaneous speed. And that is the speed at any one given moment. All right. Um, so a more practical way of thinking about that, the speed at any one given moment, well, if you're traveling in your car and you want to know how fast am I going at this particular moment, what would you do? Well, hopefully what you do is you look down at the dashboard at the speedometer. And so that's a good way of thinking about instantaneous speed. It's the reading on the speedometer. Okay. So that's the difference between average speed and instantaneous speed is that a trip will be made up of all these different instantaneous speeds, but then when we think about holistically, it's the average speed. Now, technically, the average speed should be the average of all the instantaneous speeds. But what's problematic about that? Well, if you said that there's an infinite number of instantaneous speeds, you start getting into the idea like, yeah, that's a problem. That's a very difficult mathematical process to do. So we're not going to conceptualize it like that because we're going to get ourselves into trouble if we start trying to conceptualize that as the average of all the individual speeds because there are an infinite number of them. We'd need some more math in order to do that. The answer actually to that is calculus is what we would need, but we're not going to do that. So let's go back to the original statement here. I can now say the instantaneous or the average speed, excuse me, for path one, we just calculated as 51.4 miles per hour. And if I was to do this for path two, speed two average, distance two over time two equals 200 miles over 3 hours for an average speed of 66.6 repeating miles per hour. So I could say on average, I'm going faster along path two than I am going along path one. Okay, so that's the notion. Now, oddly enough, what we don't have yet is a definition for what speed is. So let's just talk about the concept of speed itself. What is speed telling us? Well, if we look at the definition of the mathematical, rather, formula definition of average speed, we kind of get the idea. it's trying to tell us how far we're going in a certain amount of time, right? So if I look at here, what I have is a ratio. And it's a very special type of ratio. It's a ratio of how something is changing through time. And we have a name for ratios that talk about how a quantity changes over time. And those are rates. So what's speed? Speed is the rate at which distance is traveled. Very simply. And so I'm going to box that as an idea. The rate at which distance is traveled. Now, let me maybe give you those two other vocabulary words. Ratio is going to be how one quantity changes as another quantity changes, right? So if I talk about like at the supermarket for $1, I can get 4 apples. That's a ratio, $1 per 4 apples, right? But a rate specifically is how a quantity changes through time. Okay, so it's a special type of ratio. And I think a lot of people use the word rate and speed interchangeably, and that's simply not going to be true. There's a lot of different rates. Here, rate of speed is the rate at which distance is traveled. So let's bring this to velocity. Well, one of the foundational notions that we talked about here is that we have to know what type of quantity we're dealing with. And so what we said is that velocity, the most important thing we learned about it initially is that velocity is what type of quantity? Well, it is a vector quantity because it matters the direction that you're going when talking about velocity. 4 meters per second south is a very different thing than saying 4 meters per second because velocity always has directionality encoded into it. So therefore, as we made the argument before when we were talking about vectors, that if I'm going to try and talk about vectors, vectors need to be based on other vectors. So we're going to do the same sort of note sequence that we did before, but thinking how is it going to be different with velocity? And then we'll see how speed and velocity are distinct from there. So let's talk about average velocity. It's the easiest thing to talk about. So average velocity, if we look at the definition of average speed, which was the one speed you would have to go to travel to go that distance in that time. Well, I don't want to be basing average velocity on distance, right? Because distance is a scalar. So what should we base it upon? I'll let you think about that for a second. What we should be basing that on, and I'm going to like put this out as an equation, is rather than talk about distance, we should be talking about total displacement instead, right? Over total time. So that kind of uses the same sort of parallel logic, whereas speed depends upon distance, velocity depends upon displacement. So it's an equation then, average velocity, and we're going to use v for velocity, and it is a vector, is equal to total displacement. Now I'm just going to use the generic displacement vector, delta s, over total time. And I'm going to put some t's on those from subscripts, and there we go. We're going to box that. Okay, so then what is instantaneous velocity? This is going to be the velocity at any one moment, right? So in other words, it's going to answer the question, how fast and in what direction? Okay, and then we'll come back to a definition for velocity now. So velocity, if we look at the definition of speed, it's the rate at which distance is traveled. So velocity is going to be the rate at which displacement is traveled. Now, if you think about what displacement is, we can change that definition again as well. And that's going to be the rate at which the position changes. Because a change in position is displacement. Notice here, I'm not saying the rate at which displacement changes. That makes no sense. A displacement is a certain change in the position. So I wouldn't want to say the rate at which the change in the position changes. Pardon me for a second. There's a truck outside my office. Okay. All right. So that's our definition, or either of these are our definition of velocity. But why the distinction then? Well, when we come back to our original problem, then, if I wanted to talk about the average velocity for path one, it wouldn't have the same value as the average speed of path one. And why is that? Well, if you said that, I only know the distance here. What's the displacement? You're right. Let me draw in the displacement vector, which is a vector that goes from the beginning of the trip to the end of the trip. That is the total displacement vector. And as you can see, the size of that vector is very different than the total speed. From Scarsdale to Binghamton, by the way, that total displacement vector is about 160 miles at 17 degrees north of west, which is a very different thing. So if I were to look then at path one, or what is the average velocity for path one, I would have to take the total displacement for path one over the total time for path one. And so that would then be that 160 miles, literally at 17 degrees north of west, the direction comes along for the ride over 3.5 hours. And if I was to look at the average velocity for path two, I take that same total displacement because the total displacement for path two is the same as the total displacement for path one because displacement doesn't care about path over time two. And we can see that we would get yet a different number, or sorry, yeah, there we go. At 17 degrees north of west. I'm not going to do the math, but you can see that these average velocities are going to be different because the times along the path were the same. It doesn't care about the distance of the path. So I think we can see pretty clearly here that the average velocity is not the same thing as the average speed. Whereas if I take an instantaneous velocity, let's say an instantaneous velocity vector is 4 meters per second east, the magnitude of the instantaneous velocity there would be 4 meters per second. So the magnitude of the instantaneous velocity is the same thing as the magnitude, or excuse me, the magnitude of the instantaneous velocity is always the same thing as the instantaneous speed. But the magnitude of the average velocity is not going to be the same thing as the average speed because speed takes the path into account, velocity doesn't take the path into account, right? And so those are the differences between average velocity, average speed. So in this class, more often than not, we're going to be talking about velocity because we're going to be dealing with vector quantities, but sometimes we're going to want to talk about their scalar equivalents or their scalar counterparts. So hopefully that helps us out with the difference between speed and velocity, talking about instantaneous quantities and average quantities. A little muddled.